In the last two lectures, we have seen how to use the power series method to solve certain second order differential equations. The power series method is a fairly general method, but it turns out that in some cases it does not work out as well as you would expect. Let us take the example of the differential equation square minus mu square equal to 0. Okay. So, suppose you have this differential equation, then if you just use the power series method, you will say n equal to 0 to infinity C n x raised to n, and then you will say y prime and y double prime okay. Okay, now before I substitute this, I want to mention one thing is this n equal to 0 to n equal to infinity, the lower limit n equal to 0, when n is equal to 0, this term is 0 because it is multiplied by n. So, sometimes this is the non-zero terms start from n equal to 1. So, it is identically equal to this. Okay, so this is equal to this. Similarly, in this case, the term with n equal to 0 is 0, n equal to 1, then n minus 1 is 0. So, the first two terms are 0. So, this is identically equal to n equal to 2 to infinity. Is 2. Okay. So, sometimes in some books they will write this from n equal to 1 to infinity, and they will write this from n equal to 2 to infinity, but even if you write n equal to 0 to infinity, there is no harm done. Okay. So, now you take this and you substitute in these equations, and what you will get immediately is that the first term x square y double prime. So, that will give me x raised to n. Okay. I will just the second term, I will just take n equal to 0 to infinity common. The second term will give me x y prime. So, that is n c n x raised to n. Okay. The third term will give me x square minus nu square into y. So, that is I can write it as two terms. One is x square into y n c n. So, that is c n x raised to n plus 2, okay. And the other term is minus nu square c n x raised to n, okay, and this is equal to 0. Okay. Now, let us look at terms of power, terms of order. X raised to 0. Okay. So, if you look at the term of order x raised to 0, in this case n has to be 0, n has to be 0 here, n has to be here there is no term of x power 0, and here there is one term of x power 0. So, if you write that here you will get 0 plus from this again n equal to 0. So, you get 0. Here there is no term because even when n equal to 0, this starts with x square, okay, and you have minus nu square c 0, okay, equal to 0. Okay. So, nu square is some general number, and if nu is not equal to 0, then you have c 0 equal to 0. Okay. So, you get C 0 equal to 0, and you can immediately show that this implies that C 2 equal to 0 all are 0. So, C 2 will be related to C 0, because if you look at the terms of order x square if you look at the terms of order x square, okay, then you will get terms of order x square, then this will get 2 into 1 into 2 C 2 plus here you will get x square. So, n equal to 2. So, 2 C 2 plus here you will get a term when n equal to 0. So, C 0 minus nu square C 2 equal to 0. So, that implies that C 2 equal to C 0 divided by nu square minus 4. Okay. So, C 2 is equal to nu. So, this is 4 C 2. So, 4 C 2 minus nu square. So, C 2 is C 0 divided by nu square minus 4 equal to 0, and similarly you can show all the even terms go to 0. Okay. So, basically all the even terms go to 0. Now we can look at the odd terms. So, when you look at terms of x raised to 1. So, all even power terms equal to 0. Now, next you look at terms of x raised to 1. So, if you want x raised to 1, then in this case n has to be equal to 1, but if n equal to 1, this term gives 0. In this case n equal to 1 implies you have 1 C 1. So, you have C 1. Okay. In this case you can never have x raised to 1, because even if n equal to 0 you get x square, and in this case you have nu square C 1 equal to 0, and this implies C 1 times 1 minus nu square equal to 0. In general, nu square is not equal to 1. So, if you take a value of nu square which is not equal to 1, so this implies C 1 equal to 0, and this implies C 3 equal to C 5 equal to 0. So, therefore, only solution for arbitrary nu is y equal to 0. Okay, so, from these two what you will conclude is that the only possible solution for an arbitrary value of nu, okay, where nu is not equal to 0, nu is not equal to 1, okay, is when y equal to 0. Okay. So, what you realize is that if you apply the power series method in this for this differential equation, you end up with a trivial solution, that is y equal to 0. So, any homogeneous equation always has a solution y equal to 0, but that is not the solution that you are interested in. So, therefore, the power series method fails. So, you conclude that the method fails. Okay. Now, what we will do is we will modify the power series method so that you can use it for this problem, but before that we want to understand why this failed, or we want to look at some reasons why this failed. Okay. In this case your power series infinity C n x minus 0 raised to n. Okay, so I am writing my power series as an expansion about x equal to 0. So, just as you write a Taylor expansion about x equal to 0. So, I am just writing it this way. So, this is the same as this, but I just write it this way just to highlight that this is power series expansion about x equal to 0. Okay. Okay, so what we have used, what we used when we wrote the power series method is that we did a power series expansion about x equal to 0. You can also do power series about x equal to 1, x equal to 3, any number, x equal to 0.5, anything. But in this case, we used about x equal to 0, and it failed in this particular case because the coefficient of y double prime vanished at x equal to 0. Okay. So, the coefficient of y double prime is x square, okay, and when x equal to 0, x square is equal to 0. So, the coefficient of y double prime vanished at x equal to 0, therefore, the power series failed. So, hence okay. Now, in order to actually see why such a statement is true, you have to go through some exercise. You have to actually take a general power series and show, and it's possible to show that such a statement is true. We won't go into that detail. What we'll do is we'll do a small analysis here of how the coefficient of y double prime affects the nature of the solutions. So, in this case, whenever the coefficient vanishes at x equal to 0, then x equal to 0 is called a singular point. Of the second order ODE. Okay. So, whenever the coefficient of y double prime vanishes at some value of x, then that point is called a singular point of the second order ODE. Okay. So, let us look at these singular points in a little bit more detail, and what I will do in the next 15 or 20 minutes is to tell you what methods you can use whenever you have singular points in a differential equation. So, suppose you had a differential equation of the form a of x y double prime plus b of x y prime plus c of x equal to 0, c of x y equal to 0. Okay. Then such a differential equation has a solution in the form of a power series about x 0. Okay. So, this has a solution in the form of a power series about x 0, and that solution will have the form y is equal to sum over n equal to 0 to infinity C n x minus x 0 raised to n. Okay. So, this differential equation, it has a solution only if a of x 0 not equal to 0. Okay. This has a solution only if a of x 0 not equal to 0 or x 0 is not a singular point. Okay. So, such a differential equation has a solution in the form of a power series. So, you can use the power series method only if a of x 0 is not equal to 0 or x 0 is not a singular point. Okay. So, this is a statement, we will not actually prove it, but we will just take it as a given. Now, suppose a of x 0 equal to 0, suppose a of x 0 equal to 0, okay. Then let p of x is equal to b of x by a of x and q of x equal to c of x by a of x. Okay. So, you let this be this, and we also ensure that also with no common factors between p of x, q of x and a of x. Okay. So, we basically make sure that any common factors between p of x, q of x and a of x are divided out. Okay. So, now remember that at x equal to x 0, this goes to 0. Okay. So, this goes to 0 at x equal to x 0. So, therefore, at a of x 0 equal to 0. So, therefore, you would expect p of x diverges at x equal to x 0. So, unless b of x has some other factors of which also goes to 0, you would expect that p of x will go to infinity when x equal to x 0. Okay. So, if so in other words p of x goes as 1 over x minus x 0 to some power, I will call it r. Okay. Similarly, q of x, similarly you can write same thing, q of x diverges at x equal to x 0. So, q of x will go as 1 over raised to r prime. Okay. So, where r prime is some positive number. So, then when x equal to x 0, p of x goes to infinity, q of x goes to infinity. Okay. If r is a positive number, then it diverges in that form. So, now suppose r is equal to 1 and r prime less than equal to 2. Okay. So, suppose r is less than equal to 1. So, the divergence of p of x, okay, is slower, it is slower than or equal to x minus x 0, 1 over x minus x 0. So, in other words, p of x 0 diverges, or p of x diverges more slowly than 1 over x minus x 0, and q of x diverges more slowly than x minus x 0 square. Okay. That means the q of x divergence is more slow than this, that means r prime was less than or equal to 2. Okay. So, then x 0 is called a regular singular point. Okay. If this condition is satisfied, then x 0 is called a regular singular point, and for a regular singular point you can use power series. So now can use modified power series method. Okay, and in the modified power series method we use y is equal to 0 to infinity C n x raised to n plus r. Okay, n plus some number r. Okay, this r is not the same as this r. Okay, this is some other r. Okay, or if you want I can call it r double prime. Okay, and we'll see how to use this method shortly. Okay, but just to remind you once again, what we have done is we started with a differential equation. Now this differential equation has x equal to x 0 as a singular point. So it has a singular point at x 0. So you could not use a power series of this form. Okay, if x 0 was not a singular point, you would have just used this as the power series method. But since you are not able to use this, what you said is we'll look at the nature of the singular point. Okay, in order to see the nature of the singular point, you have to see what is the divergence of p of x, what is the divergence of q of x. Okay, so how do you see how p of x diverges, how q of x diverges, and if this divergence is slower than 1 over x minus x 0, and similarly this divergence is slower than 1 over x minus x 0 square, then x equal to x 0 is called a regular singular point, and we can use the modified power series method. Okay, I'll before I go into using the modified power series method, I will try to show you some examples where how you will check whether some point is a regular singular point or it is not a regular singular point. Okay, now if you have a singular point, how do you find out this r and r prime? Okay, so I'll just show you an example of that. Let's go back to the differential equation that we had. So let's consider the case where you had x square y double prime plus x y prime plus x square minus mu square y equal to 0. So let's consider this case. Now we said that we wanted to try y is equal to sum over n equal to 0 to infinity C n x raised to n. Okay, so this is same as sum over n equal to 0 to infinity C n x minus 0 raised to n. Okay, and this method failed. The reason it failed was x equal to 0 implies x square equal to 0. So the coefficient of y double prime equal to 0 at x equal to 0. Okay. So therefore this power series method failed. Now we have to find out whether this is a regular singular point or it is not a regular singular point. So what we do is we divide this plus y prime by x plus 1 minus mu square by x square y. Equal to 0. Okay, so I just divided by x square. So this implies p of x equal to 1 by x, okay, and q of x okay. Now we have to find out whether this diverges faster than 1 over x minus 0 and this diverges faster than 1 over x minus x 0 square. So you have to find out how this diverges, and clearly this is equal to 1 over x minus 0 raised to 1. So this implies r equal to 1. Okay. So r equal to 1 here. What about this case? How do we write this in terms of this this expression? Okay. So we have to look at look at what happens when x tends to 0. So, when x goes very close to 0, okay, this term becomes very large. Okay, so, when x becomes arbitrarily close to 0, this term becomes very large, this compared to this. So, this goes as minus nu square over x square as x tends to 0. Okay, so, this diverges as implies r prime equal to 2. Okay. So, r equal to 1, r prime equal to 2. So, this is a regular singular point. Okay. So, this is a regular singular point. Okay. So, so you have to analyze what is the term that is largest when x tends to 0 and x tends to 0, and that term turns out to be this. Okay, because this becomes much smaller than that, and this is proportional to 1 over x square, and so r prime equal to 2. So, since r equal to 1, r prime equal to 2, this is a regular singular point, and now that means you can use the modified power series method, which is also called the Frobenius method. Okay. So, what we will do is we will apply the Frobenius method and try to solve that differential equation. This differential equation is called Bessel's equation. Okay, and it is one of the most famous equations in applied mathematics. So, the Frobenius method, what you say is y n plus r, okay, and again this r should not be confused with this r there. So, y equal to C n x raised to n plus r. Now, what we will do is we will apply the, we will start with this series and then we will apply it and see what happens. So, this implies y prime is equal to sum over n equal to 0 to infinity n plus r C n x raised to n plus r minus 1, and y double prime okay. So, this is the first step of the Frobenius method, and then what you will do is you will substitute it in this equation. So, when you substitute this in this equation, what you will get is first term is sum over n equal to 0 to infinity C n x raised to n plus r. The second term is x times y prime, and that is okay, and the third term okay, I will write it as sum of two terms. The first term is C n x raised to 2 minus nu square, this whole thing equal to 0. Okay. So, I wrote it as 4 terms. Okay. So, so now we need to determine the value of r. So, you need to determine r, and in order to determine r, we look at the coefficient of x raised to r. X raised to r. Okay. So, if you want x raised to r in this expression, n has to be equal to 0. So, if n equal to 0, this is r minus 1, and n equal to 0. So, C 0. In this case, what you will get is n equal to 0 again. So, you will get plus r C 0 in this case if you want x raised to r, then n has to be minus 2. So, it is not possible. So, you cannot have a coefficient of x raised to r. In this case if you want x raised to r, n has to be equal to 0. So, minus nu square C 0 equal to 0. Okay. So, the coefficient of x raised to r, and this is called the indicial equation. Okay. And you can immediately see if C 0 is not equal to 0. So, we demand C 0 not equal to 0. Okay. So, we choose a value of r such that C 0 is not equal to 0. Okay, and you can do that, and what you have is r square minus r plus r minus nu square. So, r square minus nu square equal to 0 implies r equal to plus or minus nu. Okay. So, what we did is we started with this, okay, under the we demanded that C 0 is not equal to 0, and when you substitute this in the differential equation, the coefficient of x raised to r gives you a condition for r. Okay. So, what we got is r equal to plus minus nu. Okay. Now, r has to be equal to plus minus nu, and now you will have different cases, and in each case we will look at the nature of the solutions. Okay. So, I will just mention a few things about the nature of the solutions using the Frobenius method. In the particular case of the differential equation, the Bessel's equation, we saw that r has to be equal to plus minus nu. In general, the indicial equation has two roots, r 1 and r 2. Okay. In the case of Bessel's equation, r 1 was equal to nu, r 2 was equal to minus nu. Okay. And there are three cases. First case, r 1, r 2 are real and distinct. Okay. So, if these two are real and distinct, then you can have two possibilities. Y is equal to sum over x to the r 1 C n x raised to n. So, I wrote C n x raised to n plus r 1. So, I just took x raised to r 1 outside, and y is equal to x raised to r 2 sum over, I will just say m equal to 0 to infinity C m x raised to m. Okay, I can call this n also. So, basically these are the two linearly independent solutions. So, I call this y 1 y 2. So, y 1 y 2 are two So, if these two are distinct, then these two become two linearly independent solutions. There is one more condition, real, distinct and do not differ by an integer. Okay, they should be real, distinct, and they should not differ by an integer. Okay, this is the condition for you to be able to write this as linearly independent. If r 1 and r 2 differ by an integer, okay, if r 1 and r 2 differ by an integer, then it turns out that these two series become very closely related. You can write one series in terms of the other. Okay, then you lose the fact that they should be linearly independent. Okay. So, now suppose R1 equal to R2. Okay. Then one solution y is equal to x raised to r x raised to n, and we can determine the second solution by variation of parameters. Okay. So, so suppose you have one solution in this differential equation. If you have one solution, you can determine the second solution by variation of parameters. Okay. And I will leave this as an exercise to you, but you can show that the second solution looks to be of the following form. So, y 1 is this, y 2 is equal to y 1, y 1 times natural log of x plus x raised to r plus 1 sum over n equal to 0 to infinity b n x raised to n plus r. Okay. B n x raised to n, sorry, x raised to n. Okay. So, where the coefficients of b n can also be found out. Okay. So, this is a second solution. We will not go into the details of this, but essentially you can always calculate one solution using the Frobenius method. The second solution you can calculate by variation of parameters. Now, the interesting case is if r 1 minus r 2 equal to integer not equal to 0. Okay. And in this case too, you can do exactly the same thing. You can calculate the first solution, y 1 is equal to x raised to r 1 x raised to n, and y 2 you can determine by variation of parameters, and y 2 turns out to be y 1 ln of x plus x raised to r 2 sum over n equal to 0 to infinity b n x raised to n. Okay. So, so the interesting cases is we have to check whether these two roots are they real, distinct and do not differ by an integer, or whether they are the same, or if they differ by an integer. Okay. So, let us now get back to the Bessel's equation and see what we get. So, remember in the Bessel's equation was x square y double prime plus x y prime plus x square minus nu square y equal to 0, and we put y equal to sum over n equal to 0 c n x raised to n plus r, and what we got was r is equal to plus minus nu. So, therefore, r 1 minus r 2 equal to 2 nu, or absolute value of r 1 minus r 2 is 2 nu. Okay. So, actually I should write it slightly differently. I will say if r 1 equal to nu, r 2 equal to minus nu, r 1 minus r 2 equal to 2 nu. Okay. So, now, so depending on if nu is nu can be an integer, it can be 0, or it can be some fraction, or it can be a rational number which is not an integer. So, if nu equal to 0 or integer. Okay, so, if nu equal to 0 or integer, then we have to look at one of these two cases. Okay, we have to look at one of these two cases. Okay, depending on if nu is 0 or an integer. If nu is 0, then both the roots are the same, r1 equal to r2 equal to 0, and then you can write, in this case you can write the solution y1 is equal to sum over infinity Cn x raised to n plus r. Okay. Now or in this case if r1 equal to r2 equal to 0, then y1 is equal to sum over n equal to 0 to infinity Cn x raised to n. Okay. So, this is the case when nu equal to 0. Okay. So, one solution can be, you can use the, you can do this in the form of this power series, and what you can show is that you use this power series method in the usual way. Okay. So we already started with the modified power series method, and then we saw that r equal to plus minus nu, but nu was equal to 0. So, one solution can be written in terms of a power series, and this series turns out to, when you substitute this and you work it out, you will find that it leads to a convergent series. And remember what we said is that a convergent series is some series that truncates somewhere. So, instead of going from 0 to infinity, it stops at some point, and that series is called the Bessel function. This series is called Bessel function. So, this is called Bessel function of the first kind. Okay. I will not go into the details, because the way you find the Bessel function of the first kind is exactly similar to the way we found the Legendre polynomials. Okay. Just as we did the Legendre polynomials, you can show that this leads to the Bessel function of the first kind. The other solution is called Bessel function of second kind. Okay. So, the other solution that you get by variation of parameters is called Bessel function of second kind. The symbol used for Bessel function of first kind is j nu of x. Okay. So, if nu equal to 0, then this function is called j 0, Bessel function of degree 0. If nu equal to 1, it is called Bessel function of degree 1, and so on. Okay. So, so this is about how much I want to talk about the power series method. Now, in the next class, we will see an application of this power series method, and the application will be to a problem that you will encounter in your quantum mechanics courses, or you have already seen it in quantum mechanics courses. This is calculating the angular part of the wave function for a hydrogen atom problem. Okay. So, we will look at that in the next class.